The Diffusion of Pulmonary Gases, based on Chapter 4 of Desjardins' Cardiopulmonary Anatomy and Physiology. In this video, you should be able to describe Dalton's law, explain how Dalton's law relates to the partial pressure of atmospheric gases, identify the percentage and partial pressure of the gases that compose the barometric pressure. You should also be able to differentiate between pressure gradients and diffusion gradients. The student should be able to identify the partial pressure of the gases in the air, alveoli, and blood, calculate the ideal gas equation, and name the 9 major structures of the alveolar capillary membrane through which a gas molecule must diffuse. Also, in this video, students will learn how to describe how oxygen and carbon dioxide normally diffuse across the alveolar capillary membrane, explain how Fick's law relates to gas diffusion, describe how Henry's and Graham's law relate to diffusion constants in Fick's law, define perfusion limited, and explain how it relates to a gas like nitrous oxide. Define diffusion limited and explain how it relates to a gas like carbon monoxide. And describe how oxygen can be classified as either perfusion or diffusion limited. Let's begin with Dalton's law of partial pressures. Dalton's law states the total pressure exerted by a mixture of gases, like air, is equal to the sum of each individual pressure of the gas in the mixture. Pressure exerted by each gas, its partial pressure, is directly proportional to the percentage of that gas in the gas mix. For example, a gas mixture of gas A and gas B. Gas A has 10 molecules and exerts a pressure of 10. Gas B has only 5 molecules and exerts a pressure of 5. When the gases are mixed together for gas A plus B, the pressure together is 15. The sum of the two gases, 10 plus 5, is equal to the sum of 15. Remember that the total pressure exerted by a mixture of gases is equal to the sum of the pressures exerted independently by each gas in the mixture. Partial pressures of atmospheric gases. Earth's atmospheric gases consist of nitrogen, N2, oxygen, O2, carbon dioxide, CO2, and other trace gases like argon. Nitrogen consists of about 78% of the total barometric pressure of 760 torr. Oxygen is 21% of atmospheric gases. Carbon dioxide is 0.03% of atmospheric gases, and other trace gases are about 0.9% of the total atmospheric gases. Because partial pressure of each gas that surrounds the Earth is directly related to its concentration relative to the barometric pressure, or P sub B, partial pressure of each gas can easily be determined by multiplying the barometric pressure by the percentage of gas in the atmosphere. For example, because the percentage of oxygen in the atmosphere is approximately 21%, and assuming that normal barometric pressure is 760 millimeters of mercury at sea level, the partial pressure of oxygen is calculated as follows: 0.21, or 21%, times 760 is equal to 159.6 millimeters of mercury. I want you to try this now on your calculator and see how you do. The partial pressure of each atmospheric gas, nitrogen, oxygen, carbon dioxide, and some trace gases, together make a total atmospheric pressure of 760 millimeters of mercury at sea level. As the density of the atmospheric gases diminish, the partial pressure exerted by each gas, for example oxygen, also decreases. It is important to remember that even though barometric pressure decreases with altitude, concentration of all atmospheric gases remains the same at both high and low elevations. In other words, the percentage of oxygen is always approximately 21%, both at sea level, like in Seattle, Washington, or at the top of Mount Everest. What changes at different altitudes are the partial pressures of the atmospheric gases. It should also be noted that moving in an opposite direction has a reverse effect. That is, atmospheric pressure is increased by 1 atmosphere, 760 millimeters of mercury, for every 33 feet of descent under the water. For example, at 99 feet below sea level, the total pressure exerted on the body is equal to 4 atmospheres, 3 atmospheres under the water, and the 1 atmosphere above the water. This means the partial pressure of oxygen increases from about 159 millimeters of mercury to 636 millimeters of mercury. So, at a depth of 33 feet under the water, how many atmospheres do you have on your head? I'm going to give you a minute to think about it. If you said 2 atmospheres, you're absolutely correct. You have the 1 atmosphere above the water and the 1 atmosphere at a depth of 33 feet below the water. Remember that atmospheric pressure increases by 1 atmosphere for every 33 feet of descent in water below sea level. So let's talk about the difference between pressure gradients and diffusion gradients. A pressure gradient is defined as the movement of gas from an area of high pressure or high concentration to an area of low pressure or low concentration. A pressure gradient is the primary mechanism responsible for moving air in and out of the lungs during ventilation. It's important to remember that the pressure gradients generated during ventilation always move a volume of gas in the same direction, either into or out of the lungs. That means that all the little individual gases, oxygen, carbon dioxide, trace gases, nitrogen, all move in the same direction, either into the lungs or out of the lungs as a unit. On the other hand, gas diffusion is a little bit different. Gas diffusion is defined as the movement of individual gas molecules from an area of high pressure or high concentration to an area of low pressure or low concentration. In other words, each individual gas, nitrogen, oxygen, carbon dioxide, trace gases, can move independently from the other gas molecules from an area of high pressure to an area of low pressure. Individual gas partial pressure differences are known as diffusion gradients, and kinetic energy is the driving force responsible for diffusion, for those molecules to go from an area of high concentration to an area of low concentration. This means that when a volume of gas reaches its destination, for example the alveoli, by means of a pressure gradient, or the alveolar by way of pulmonary capillary blood flow, each individual gas can move according to its own diffusion gradient. So oxygen can move out of the alveolus and diffuse across the alveolar capillary membrane and into the capillary, where the concentration of oxygen is lower. However, the carbon dioxide can move from an area of high concentration to an area of low concentration, so it will move out of the capillary and into the alveolus until equilibrium is reached. This table, Table 4.1 on page 190 of your book, shows the partial pressure of gases in a dry air, alveolar gas, arterial blood, and venous blood. Please note that even though the total barometric pressure is the same in the atmosphere and the alveoli, the partial pressure of oxygen in the atmosphere is 159 torr and is significantly higher than the partial pressure of oxygen in the alveoli at just 100 torr. This is because alveolar oxygen must mix or compete in terms of partial pressures with alveolar carbon dioxide pressure of about 40 millimeters of mercury and alveolar water vapor pressure about 47 millimeters of mercury. These are not nearly as high in the atmosphere. In short, by the time the oxygen molecules reach the alveoli, they are diluted by the addition of both carbon dioxide and oxygen molecules. This leads to a decrease in the partial pressure of oxygen in the alveoli. Depending on the surrounding temperature and pressure, water can exist as a liquid, gas, or solid. Water in gaseous form is called water vapor or molecular water. When water vapor is present in a volume of gas, it behaves according to the gas laws and exerts a partial pressure. Because alveolar gas is 100% humidified or saturated at body temperature, the alveolar gas is assumed to have an absolute humidity of 44 milligrams per liter of water and a water vapor pressure of 47 millimeters of mercury, regardless of the humidity outside. Notice that absolute humidity reflects a volume or amount of water in the air, and the water vapor pressure is the pressure that water exerts. Clinically, the alveolar oxygen tension, or P big AO2, can be calculated from the ideal alveolar gas equation. This is a useful clinical approximation of how much partial pressure of oxygen is actually in the alveoli. P big AO2 is the partial pressure of oxygen in the alveoli. P sub B is the barometric pressure. pH2O is the partial pressure of water vapor in the alveolus, equal to 47 millimeters of mercury. FiO2 is the fractional concentration of inspired oxygen. And P(a)O2 is the partial pressure of arterial carbon dioxide. Please note that the big A denotes alveolus and the little a denotes arterial. The number 1.25 is a factor that adjusts for alterations in oxygen tension due to variations in the respiratory exchange ratio, which is a ratio of the amount of oxygen that moves into the pulmonary capillary blood as compared to the amount of carbon dioxide that moves out of pulmonary capillary blood and into the alveoli. Normally, about 200 milliliters per minute of carbon dioxide move into the alveoli, while about 250 milliliters per minute move into the pulmonary capillary blood, making the respiratory exchange ratio about 0.8, or if you're multiplying, 1.25. Let's look at this in action. If a patient is receiving a fraction of inspired oxygen of 40% or 0.40 on a day when the barometric pressure is 755 millimeters of mercury, and if the pressure of arterial carbon dioxide is 55 millimeters of mercury, then the patient's alveolar oxygen tension, or P big AO2, can be calculated as follows. Barometric pressure, 755, minus 47, which is the pressure of water vapor, times 0.40 is equal to 283.2. That's just the first half. Then we need to take 55 times 1.25, which is equal to 68.75. 283.2 minus 68.75 is equal to 214.45. Clinically, when the PaCO2 is less than 60 millimeters of mercury, remember, less than the PaCO2, when the carbon dioxide in the arterial blood is less than 60 millimeters of mercury. When the patient is receiving oxygen, a fraction of inspired oxygen that is greater than 60%, the following simplified equation may be used. Pressure of alveolar oxygen is equal to barometric pressure minus water vapor pressure, time fraction of inspiratory oxygen minus CO2. The diffusion of gas takes place according to Fick's law, which is written as follows. Dot V gas is equal to A times D times P1 minus P2 divided by T, where V dot gas is the amount of gas that diffuses from one point to another. A is the surface area, D is the diffusion constant, P1 minus P2 is the difference in partial pressures between 2 points, and T is the thickness. The law states that the rate of gas diffusion across a sheet of tissue is directly proportional to the surface area of the tissue and the diffusion constants, and to the difference in partial pressure of the gas between the two sides of the tissue, and is inversely proportional to the thickness of the tissue. The diffusion constant D noted in Fick's law is determined by Henry's law and Graham's law. Henry's law states that the amount of gas that dissolves in a liquid at a given temperature is proportional to the partial pressure of the gas. The amount of gas that can be dissolved by 1 milliliter of a given liquid at standard pressure, 760 millimeters of mercury, and specified temperature is known as the solubility coefficient of the liquid. At 37 degrees centigrade and 760 millimeters of mercury pressure, the solubility coefficient of oxygen is 0.0244 milliliters per millimeter of mercury per milliliter of water. If the temperature rises, the solubility coefficient decreases in value. On the basis of solubility coefficients of oxygen and carbon dioxide, the solubility of carbon dioxide is 24, the solubility of oxygen is 1. It can be seen that in a liquid medium, like the alveolar capillary membrane, carbon dioxide is much more soluble than oxygen. Graham's law states that the rate of diffusion through a gas in a liquid is directly proportional to the solubility coefficient of the gas and indirectly proportional to the square root of the gram molecular weight of the gas. In comparing the relative rates of diffusion to oxygen, gram molecular weight 32, and carbon dioxide, gram molecular weight 44, it can be seen that because oxygen is the lighter gas, it moves faster than carbon dioxide. By combining Graham's and Henry's law, it can be said that the rates of diffusion of two gases are directly proportional to the ratio of their solubility coefficients and inversely proportional to the ratio of their gram molecular weights. For example, when the two laws are used to determine the relative rates of diffusion of carbon dioxide and oxygen, it can be seen that carbon dioxide diffuses about 20 times faster than oxygen. Clinically, Fick's law applies to the following general statements. The area A component of the law is verified in that a decreased alveolar surface area, like that caused by alveolar collapse or alveolar fluid, decreases the ability of oxygen to enter the pulmonary capillary blood. The P1 minus P2 portion of the law is confirmed in that a decreased alveolar oxygen pressure, like P big A O2 or P1, caused by high altitudes or alveolar hyperventilation, reduces the diffusion of oxygen into the pulmonary capillary blood. And lastly, the thickness or T factor is confirmed in that an increased alveolar tissue thickness caused by alveolar fibrosis or pulmonary alveolar edema reduces the movement of oxygen across the alveolar capillary membrane. Perfusion limited. Perfusion limited means the movement of gas across the alveolar wall is a function of how much blood flows past the alveolus. The more blood that flows past, the more diffusion that happens. No blood flowing past, no perfusion. Diffusion limited means that the movement of gas across the alveolar wall is a function of how intact the alveolar capillary membrane itself is. If the alveolar capillary membrane is functioning normally, gas will move across the membrane quickly and in a normal fashion. If the alveolar capillary membrane is damaged in any way, scarred, if there's fluid, anything in the way, then movement of gas across the alveolar wall will be slowed or stalled. Thank you for your time and attention. This is the end of our video about diffusion of pulmonary gases. Have a great evening.